So today we want to look at several of these concepts that have to do with mechanics, and we're going to be focusing really on three of them. One is the idea of speed and defining speed. Well, speed is the distance something has moved over the time that it accomplished that, so the time that is passed. So the distance divided by the time that passed. If it's 60 miles in 1 hour, then we have 60 miles per hour. That's easy to remember. So you're not going to have any trouble thinking of what speed is. Okay. Give you an example. Let's work a problem dealing with speed. Just give you an example. Go ahead and write that down in your notes, and let's work a problem really about speed. So let's say if it takes a car say 4 seconds to travel 100 meters. What is the average speed? Let's ask that. What is the average speed? Okay, so we want to use our equation. We say speed is the distance divided by the time. So we would say the distance it's going is 100 meters, and it does it in 4 seconds. So the speed would be, you do the division, 25 meters per second. There's the speed of that car. That's the average speed as it travels a certain distance over a certain time. Well, velocity is a lot like speed, except velocity always has a direction. So the object having a velocity has a direction. So like we said in the last tape, it is a vector. Okay, there's a distance. Okay, so it's a vector problem or a vector concept. So velocity is equal to the distance divided by the time, and it's worked much like speed. Let's say the velocity of a car traveling down the freeway is let's say, is the distance. It travels 200 miles in 2 hours. Okay, so you have 200 miles in or divided by 2 hours. And you get 100 miles per hour, don't you? Now that's the velocity, that's the speed that it's going, but there's a distance component. There's a vector aspect that has to do with velocity. So let's just draw a vector in there. Here's a vector. Now that's giving us a direction as well as a velocity. Now we get to acceleration, and acceleration is related to this. It really means how does speed change over time, or how speed changes in a given time frame. Okay, so the equation for acceleration is equal to the change. We use a delta, Greek delta. Those of you in ancient history Know what that is, right? So the delta V, the change in velocity over the time. So let's just make a note. Delta means a change. Or you could even say it means a difference. You work a difference out. Okay, so let's say as an example, as we think of acceleration. Now all of this is in your book, and of course you've read that section. So if some of this is not gelling real well, or if this looks like, wow, I didn't get this at all when I read it, hey, that happens. I've done that a bunch of times. Go back over it, reread it, and make sure that it makes sense to you. Now remember, acceleration is also a vector factor. It's related to the not just distance and time, but it's got a direction component. So it's got a vector component as well. So acceleration would be the change in velocity divided by the time. So here's an example. A van is, let's say it moves at 10 meters per second. So that's its velocity. It's moving in a certain direction. And it accelerates to 30 meters per second. So it's accelerated up, and it does that over a period of time. In 10 seconds, it makes this acceleration. So it's not it's not a big jump. It takes 10 seconds for it to go 30 meters per second. And so the question is, how fast was the acceleration? How fast was the acceleration? Okay, so let's just do that. I think we can do that problem. So acceleration is equal to the change in velocity. So we've gone from 10 to 30. We're going positive, right? We're going up. It's a positive movement. It's going from 10 up to 30. So what is that? 10 to 30 is 20. The change, or the difference, between 10 meters per second and 30 meters per second is 20 meters per second. Okay, so there's your delta V, your change in V. And of course you want to divide now by t. And so how fast does it do this? It does it over 10 seconds. Okay, how much time, I should say, not how fast, but what is the time involved? So you have a 10-second period. It's increasing its speed by 20 meters per second. So you do the math, and you get 20 divided by 10 is 2. And you get meters per second per second. And that's what acceleration is. It's how much is something increasing its velocity, meters per second, and over how many seconds? Per second. So in 10 seconds, it's going up 20 miles or meters per second. And we can see that that's pretty easy. It's 2 meters per second every second for 10 seconds. So there's a total of 20. So it's average acceleration. Notice this, got to be an average. There might be some seconds it's going a little bit faster, some seconds it's going a little bit slower, but the average is 2 meters per second per second. Okay, that would be its acceleration. All right, let's go ahead and go to this other side and work on kind of a new concept, and that is we want to look at deceleration now. And of course, deceleration would be something that's slowing down. So deceleration is kind of the opposite of acceleration. Deceleration would be something that's slowing or stops. So something decelerates, you're looking at it, how much is it decreasing its speed over a period of time, right? Okay, so let's say that it's a van is traveling at 40 meters per second, okay? And it stops. It stops in 5 seconds. What is its deceleration? Well, you would say acceleration, of course, is the change in velocity over time, or delta V over t. So we can see that the change in velocity is going from 40 and it stops, right? So it's going to go to 0, right? So it goes from 40 to 0, but now it's not a positive number, it's a negative number. It's going to have a negative delta velocity is negative 40 meters per second, and it does that in 5, and so the time involved is 5 seconds. Okay, so what's happening is as it slows down, it takes it 5 seconds, 5 goes into 40, minus 40, 8 times, so we have a minus 8 meters per second per second. So minus 8 meters per second per second. So 40 divided by 5 is 8, and we have a negative in front, so it's a minus 8 meters per second per second. So that means that each second for 5 seconds, it's slowing down 8 meters, and that's, you can see where that's happening. It's got a minus number. It's going slower. So that's how you would work a deceleration equation. So now, one of the things that we want to also study is the y. So this is how it acts over time. So that's the kinematics. But we also want to look at dynamics. Why is that happening? Why does something slow down as it decelerates? What are the laws that govern that motion? So Isaac Newton, developed 3 laws, and he calls them the 3 laws of motion. Newton's 3 laws of motion, and this is really good stuff. This is neat to consider because it all fits with our experience, and we see it around us. So his first law, law number 1, he talks about an object will stay in motion or it'll stay at rest, whatever it's doing. If it's sitting on the table, it's at rest. If it's flying through the air, it's in motion. But it says that an object will stay in motion or stay at rest unless it's acted on by an outside force. So let's write that down here. An object will stay in motion or remain at rest unless acted on by an outside force. Okay? And so there's a tendency of something to stay at rest. You know, if something is not moving, it's at rest, right? So it's sitting on the table, it's sitting on the ground, and it's not going to move unless something acts on it, an outside force acts on it to make it move. Okay? So let's say we have a baseball. Here's the ground. Okay, there's the ground. And this baseball is thrown in a direction. And we watch the travel path, and we see that it goes down and eventually it hits the ground down here. Okay, now the baseball, though, was thrown in this direction. Why does it not just keep going in that direction? Now, his law says it will move in the same direction unless acted on by an outside force. Okay, so you all have thrown a ball and you've seen it hit the ground. None of you have seen a ball. Maybe Christian has, I don't know, or Josh, where you throw a ball and it doesn't hit the ground. That would be cool, wouldn't it? Wouldn't that be great? So here, though, we see the ball and it acts like it has for most of us. We watch it, it hits the ground at some point. So it's not going in a straight line. It's not moving in the same direction. But it's being acted on by a couple forces, isn't it? So it has two forces that are making it hit the ground. And all of you can see gravity is one of them, right? So gravity is pulling the smaller object. The ball is being pulled toward the ground. Gravity is acting on it. Remember, gravity is an attractive force. It's an attraction between two bodies that have mass. And of course, the Earth is a gigantic, massive body. It's pulling, it's attracting the ball towards it. So that's part of it. What's the second force, though, acting on it? Yeah, you got it. It's friction. The friction of the air. So as it's thrown through the air itself is slowing it down. And we encounter that when we run with a flag in our hand, or we run with a kite behind us. We feel the tug of the air on the flag or the kite. That's friction. Okay, so that's another force. So that's why the ball does fall to the ground. Now his second law of motion is, he says that a force is equal to the mass of an object times its acceleration. So the force, F, is equal to m times its acceleration, m times a. All right? So if we asked you how much force is required to accelerate a big car 20 meters per second. How much force, let's write that out. How much force is needed to accelerate or move a big car, not a small car, but a large car. And let's go ahead and define what is a large car. We're going to say, okay, 2,000 kilograms. But we want to accelerate a big car 20 meters per second. Okay? So, force is equal to the mass times the acceleration. Okay, what is the mass? The mass is 2,000 kilograms, and we're going to multiply by acceleration. Acceleration is 20 meters per second. Okay, so I'm going to get 2,000 times 20. That's going to be 80,000 I'm sorry, did I say 80? Wow, that's wrong. Let me do that again. Come on, Mr. K. 40,000. There you go. 40,000. 2 times 2 is 4. And we've got kilogram times meters. So we have kilogram meters divided by seconds. Give me a little more room here. Divided by seconds. There you go. So the answer is that's the amount of force needed to move that car. Okay. And we meant to put a second squared here, which I have noticed right now I didn't put. So the acceleration, remember acceleration is always meters per second. Okay, so don't forget that. That's second squared. And so we'll end up with second squared down here. So when we have a kilogram meter over second squared, that's what a newton is. A newton is a unit of force. It is 1 kilogram meter per second, so second squared. So we're going to need 40,000 newtons to move that car so that it's going 20 meters per second. Okay, so that's how you work using Newton's second law. We're going to go now to our third tape.